So let's spend a little bit of time talking about adjoint for. Let's start with steady PDEs. Actually, so before doing this, I think it's important to actually have some of interpretation of what the adjoint field is doing. So the adjoint field, by definition, it is equal to. So the adjoint field by definition is this, right? So delta J is equal to partial J partial U times delta U plus partial J partial S. Then I add an adjoint field and look at how much, multiply the adjoint field with a derivative of this constraint. All right, so the adjoint field is actually the sensitivity of my objective function to how much the constraint is not satisfied. So if the constraint is exactly satisfied, the adjoint is just a mathematical value that we use to cancel a bunch of terms, right? It doesn't have much physical meaning. But it has physical meaning once you consider this constraint is actually not exactly satisfied. What if my constraint, if what I introduce another value in the equation is g of us not equal to 0, but plus epsilon equal to 0, right? So then I would have an epsilon inside here. And you can see that the u hat is simply the derivative of j, is how much this delta j is going to be influenced by an epsilon. All right. So that is important when we interpret the adjoint field of some physical differential equations. So for example, if you have this is the flow over an airfoil, and we are looking at the adjoint solution here. It is the adjoint term that is the Lagrange multiplier that gets multiplied on the x momentum equation. Right. So the flow the equation we are solving is basically conservation of mass, momentum in x, y, z direction, and also energy. So like every single equation gets a Lagrange multiplier. And this is the Lagrange multiplier we ended up solving for, that is multiplied on the x momentum. It basically tells you what is the sensitivity of the objective function to a disturbance or a source term that is added to the x momentum equation. So for example, here you get a blue stripe over here, right? That means, here the objective function is how much drag I have on the airfoil. So the blue means that if I put a source term in the x momentum equation, so if I push here, if I have some magical force that pushes the fluid towards the x direction in the blue region, I'm going to actually do actually the other way. So the epsilon, right? So if I introduce an epsilon in the x momentum equation, that is like having a negative epsilon on the right hand side, right? So it's actually the sensitivity to a negative. So that means if I have if I push on the negative x direction, it will decrease my drag. So that's because here is where the like upstream of the stagnation point, right? So if I pull here, I get less stagnation pressure, so I have less drag. While here in the red region, it's interesting because that means if I pull back here in the red region, it will actually increase my drag. So why is that the case? Well, in this case, the flow is probably have a slightly separation near the trailing edge. So if you pull the fluid over here, the boundary layer is going to separate even earlier and introduce a larger pressure drag. So there is a lot of information such as this you can actually see from an adjoint solution like that. So how is this adjoint equation derived for a steady state PDE? Let's start by introducing, for example, df of u dx. Let's just think of a two-dimensional PDE. dfy of u dy equal to 0. Okay, so this is actually the case if you solve the Euler equation in 2 dimensions. So this is our differential equation. And let's say our objective function. Let's think of a case where the objective function is defined just like in our case, defined on the boundary, right? Because if we want to evaluate a drag or lift, the objective function is going to be a function of the flow field on the boundary. Let's say ju ds. Okay, is it clear like what we're doing here? And just to give you an example of how you derive adjoint for PDEs. And if you have other cases, so for PDEs, it's very hard to have a general derivation that covers every single PDE. So if you have a PDE, you probably have to go through the process again to derive what the adjoint equation is for that particular PDE. It's a little bit different from like the backpropagation case where you can have a single formula that can deal with everything. That's why, like, if you use TensorFlow or something, you don't even have to do any math. You just program whatever formula you use to do the calculation, and the adjoint is going to be computed for you at the background. You don't even know it's doing that, right? So, but for PDEs, you actually have to know how to derive the adjoint, how to do all the math to get the adjoint equation for that PDE. So if I have an objective function that is defined only on the boundary, and the next step is to linearize things. So delta j is going to be integration on the boundary, partial j, partial u, delta u on the boundary. And I'm going to add an integration on the whole boundary of an adjoint field dot with a linearized differential equation. So partial let me just say df du dfx du delta u dx plus dfy du delta u dy. This is equal over the entire x and y domain is equal to 0, right? So this is introducing the Lagrange multiplier as a function of space. Just like in the ODE case, we introduce u hat as a function of time. In our PDE, we introduce, this is y. We introduce u hat as a function of x and y. Okay, so next step is what? What do we want to cancel? Pardon? Delta u's, right. And I forget to introduce any dependence on the parameter. So the fluxes has to be a function of the parameter, and here we have additional terms, partial f x, partial s ds, dx plus partial fy, s and delta s. Okay. So we want to cancel the delta u's. And now this delta u's lives inside derivatives. What do we use? Integration by parts, right? And the integration by parts, for example, of one term, xy times this x derivative term is going to become what? So first of all, integration by parts in 2D is going to give us a boundary integral, right? And right, so let's see. So I should actually first of all be writing this in a divergence, or is it divergence or gradient? Yes, I should be writing this in a divergence form. Right. So anyway, so let's first do the integration parts in first the x direction. It's a little bit easier than writing this in the divergence form. So we'll have u hat times partial fx partial u times delta u, and times the x direction normal on the boundary, right? Not on the boundary, but integrated over the boundary. ds, and the minus integration on the boundary, first of all this term, and times the x derivative of u hat. So here we have successfully pulled this delta u out of this differential operator, right? So I probably don't have time to do all of this, but what's next is to pull delta u also out of this, and that combines with delta u over here to form the adjoint equation. And the adjoint equation is something like this. It's something like partial fx partial u transpose, okay, times partial u hat partial x plus partial fy partial u transpose times partial u hat partial y, and because of all the negative signs, this is going to be equal to whatever that is multiplied with delta u here, partial j partial u transpose. So you solve this adjoint equation. That is going to help you cancel out all these delta u terms, and then you substitute it in the only remaining term of this integral, which is integral of the adjoint times these terms that does not depend on delta u. That gives you the gradient of my objective function to the axis. It turns out to be a volume integral, right? You need to integrate the adjoint field times the partial derivative of the fluxes over the entire space. Although my objective function is defined on the boundary. Okay, actually that's the adjoint equation. In this case, I actually have a homogeneous adjoint equation, sorry. So because this is only defined on the boundary, I have no right-hand side. And it's the boundary condition of the adjoint is going to be cancelled in this term, right? So it's these terms that comes out of the integration by parts that are responsible for cancelling the term in the objective function. So I would have a non-trivial boundary condition for the adjoint, and that drives the adjoint field in the interior of the domain to be non-zero, and that non-zero adjoint needs to be integrated to get the derivative of the objective function to the parameters. All right. So I'll take any remaining questions from here. Oh, let me actually, sorry, I should come back to the question. So once we compute the gradient, we can do optimization with it, and we can also do uncertainty quantification with it, because that gradient also quantifies how a small change in the parameter, small variations in the parameter is going to affect the objective function. Right, so if your question is not optimization, but how small variations of the parameters on certain parameters going to affect your quantities of interest, that gradient also is going to tell you a lot of information, but only in the local region of the parameter space.